Hey guys, welcome back to Math from my desk. In today's video, I will be solving for the range equation in projectile motion. So I'm basically solving for delta x here. And the way I'm going to do this is I'm going to be using these two uniform accelerated motion equations and using here some vector components. So let's go ahead and start. So as you can see here, we have the initial velocity v0, and we have a ball here. It's launched at an angle with that initial velocity. And what we're going to do is we're going to break down the components, the vector components of this velocity. So we have the velocity initial in the y direction and the velocity initial in the x direction. So using some trigonometry, we know that sine theta is equal to the opposite side. In this case, the side opposite to this angle is v0y, divided by the adjacent side. In this case, that is simply v0. And so if we rearrange this equation to solve for v0y, we end up that v0y is equal to v0 times sine theta. And we can use the same method with cosine theta to figure out that v0x is equal to v0 cosine theta. And so this right here is going to be helpful in me trying to solve for this delta x here. So let's go ahead and start. So the first thing I'm going to do is I'm going to use this equation right here. The delta y is equal to v0y times delta t minus 1/2 g times delta t squared. So let me specify some things here. Why is it minus g here? That is simply because the acceleration in the y direction is equal to negative g, where g is the gravity, which is 9.8 meters per second squared. Why is it negative? Simply because we're going down. This is why. And so this right here is the acceleration in the y direction, and the acceleration in the x direction in projectile motion is always equal to 0 meters per second squared. So these are some things that we need to keep in mind here. So now let's go ahead and start solving for delta t here in this equation. So then we can plug it into the equation here for delta x. So let's go ahead and do that. But the first thing we need to recognize is that this delta y here, we're going to want that to be 0. And why is that? Because we're solving for the range here, so delta x. So basically when the ball reaches the ground, and when the ball reaches the ground, it has no vertical position. I mean, it has a vertical position where that position is equal to 0, which is what we want here. We want delta y to equal to 0. So what we're going to do is we're going to move this 1/2 g times delta t squared to the other side. So what we end up with is 1/2 g delta t squared is equal to v0y times delta t. We can divide both sides by delta t to get rid of this squared right here and this delta t. So what we end up with is that 1/2 g times delta t is equal to v0y, where we just figured out that v0y is equal to v0 sine theta. So now if we want to solve for delta t, we're going to multiply both sides by 2, and we're going to divide both sides by g. So we end up with delta t is equal to 2 v0 sine theta divided by g. All right, now we're going to go ahead and plug this into this equation for delta x. So let me go ahead and flip the page real quick. So we have 2 v0 sine theta divided by g. So delta x first and foremost is equal to v0 x times delta t. We just figured out that delta t is equal to, we said v0, hold on. We said 2 v0 sine theta divided by g. So we have 2 v0 sine theta divided by g. And what we need to recognize is that we also figured out that v0 x, as we can see here, is equal to v0 cosine theta. So we can plug that in here. So we have delta x is equal to v0 cosine theta times v0 sine theta, and we have a 2 here. All of this divided by g. We have 2 v0s here, so we can combine them to get v0 squared. So we have delta x is equal to 2 times v0 squared times cosine theta times sine theta divided by g. And what we can recognize to make this more simple is that we have this double angle identity in trigonometry, that 2 sine theta times cosine theta is equal to sine of 2 theta. And I can go ahead and prove this separately in a different video. If you would like me to do so, please leave a comment. So I can go ahead and replace this 2 cosine theta sine theta by simply sine 2 theta. So what I end up with at the end is that delta x is equal to v naught squared times sine of 2 theta divided by g. And that is the equation for the range, the horizontal range in projectile motion. Thank you for watching this video.